Okay, everyone, good morning. Welcome to NDC Oslo in Oslo. This talk is called The Power of Composition. And my name is Scott Wlaschin, and I have a website, fsharpforfunandprofit.com. As you can guess, that's mostly about F#. I'll be using C# and F# code, mostly F# code examples, but these concepts work for almost any programming language. For example, there's a lot of people doing this kind of thing in JavaScript, PHP, Ruby, Python, and so on. Right, so I am going to talk about a couple of things. First, I'm going to talk about the philosophy of composition. And there's a certain way of thinking about doing things, and I just want to kind of really hammer that home because what I'm going to be talking about all the time here. I'm going to talk about functional programming, some ideas about functional programming, which is functions and how to compose them, and types and how to compose them. So I'm assuming that we're using a statically typed functional programming language. If you're using a non-dynamic language like JavaScript, a lot of this doesn't apply in the same way. And then we'll actually have some examples of how to do composition. So we'll start with some Roman numerals. We'll do a functional version of FizzBuzz. And then we will talk about monads. And then I'll show you how you can build a web service using just composition with no classes, no mutability, nothing like that. So yeah, everyone's going to be scared about the monad bit, and hopefully it won't be so scary when we get there. So let's start with philosophy. So there's some important things that you need to have before you can understand how composition works. This is critical. First of all, you have to have been a child at some point. Very important. You have to have played with Lego. And it also helps if you have ever played with a toy train set. So these are kind of the prerequisites. If you haven't done these things, then I highly suggest you go and play with some Lego and you play with some toy trains. And in fact, you don't actually have to have been an adult. There's a child, there are quite a few adults who still play with Lego. If you Google adult friends of Lego, you will see a lot of interesting things. So hopefully all of you have met the requirements for understanding composition. And so if you have, then the rest of this will be very easy. So let's start with the Lego philosophy. So Lego actually has a philosophy, which is why it's such a great thing to use, because all the pieces are designed to be connected. Now, as I talk about Lego, every time I talk about Lego, you think about programming, okay? So I'm going to make an analogy very soon. So all the pieces are designed to be connected. All the pieces are reusable. And if you connect any two pieces together, you get another piece that can be connected. Okay, so let's go into this. All the Lego pieces have little bumps on them, right? And when they design a new Lego piece, they always put a bump on it because they know that this piece is going to be reused with other Lego pieces. So when you design a Lego piece, you think about how it's going to be reused. And when we design our programs, we want to think about our components of our programs. We want to think about how they get reused. And the other thing, of course, is that Lego can be taken apart and built one thing and then use the same pieces to build something else. And this works because the Lego pieces are self-contained. They do not have any strings attached, literally, which means that you don't have to like disentangle them before you can reuse them. Now, if they had like strings attached or electrical cables or something, they would be really hard to reuse them. But each piece is completely independent. So from a programming point of view, we want to have pieces of our program which are completely independent that can be reused. And if you ever think about like a method refactoring where you have to pull out a method because it's tangled up with other code, methods are not reusable this way. Right. Here is how you build big things out of small things using Lego. You connect two pieces together and you get another piece. And once you've put two things together, you don't have to stop. You can keep adding and adding and adding. And you never have to stop because no matter what you do, there's always some more bumps that you can add something to. And that's a really important part. You never like hit a brick wall and you have to use an adapter pattern or a bridge pattern or something Lego is always connectable. So making big things from small things, this is what you get. That's awesome. And this is the power of composition. That's the buzzword. I'm going to say the power of composition over and over. It's a great tool. All right, now let's look at wooden railways. Hopefully everyone has played with one of these. They're also a lot of fun. Again, all the pieces are designed to be connected. All the pieces are reusable. If you connect two pieces together, you get another piece that can be connected. So every single piece is designed to be connected. They all have the little bumps sticking out, or the holes in them. I don't know what you call them. Again, they're reusable. You can take them apart and stick them back together again. And they are designed to be reusable from the very beginning. And if you do connect two pieces, you kind of get another piece. It's not exactly a piece, but you get another segment of track that can be connected to other segments of track. And again, you can keep adding and adding. There's nothing that stops you making a really, really long piece of track. You don't run into any kind of artificial barriers. So, making big things from small things. Boom. This is a big railway model. So that's the power of composition. All right, so now I'm going to say that if you understand Lego and you understand toy railways, you know everything you need to know about composition, because what it is just taking these same principles and applying them to programming. So that's what we're going to be talking about in the rest of the talk. So let's talk about functional programming now. What are the concepts of functional programming and how do they relate to this idea of composition? So I'm going to talk about 4 ideas. First of all, that functions are things, right? So I'm going to use a little railway analogy for talking about functions. And the way we build bigger functions is using composition. We're going to use the Lego approach to build bigger functions. Now, if you're coming from an object-oriented world with static typing like C# or Java, it's very important to know that types are not classes. They're more like sets. And I will have a little section explaining that bit too. And in a functional programming language, you build bigger types from smaller types using composition, just like you do with Lego. So again, we're using this compositional approach to build big things from small things. Right, so let's start with functions as things. So this is something that people sometimes have a hard time with, but it's actually pretty straightforward. A function is just a thing. I'm going to use the railway analogy. So here's a little bit of railway track, and imagine there's a tunnel on the railway track. I call this the tunnel of transformation. We have, in this case, we have an apple going into the tunnel, and it goes out as a banana. So this is a function that turns apples into bananas. Yeah, what can I say? Now, the thing about a function is it's a standalone thing. It's not attached to a class. So just like a little bit of railway track, I can move it around and put it anywhere I need it. And so a standalone thing is another word for a reusable thing, because there's no strings attached. I can everything it needs is provided on the input. So it's not kind of tied into a dependency on a class or something else. No global variables, nothing like that. So no strings attached is very good. Now, the other thing about a function being a thing is it can be used as inputs and outputs to other functions. So just like a string or an int is a thing that you can pass around, a function is a thing that you can pass around. So a function can be used as a parameter. So let's look at some examples. Here is a function with a normal input, like say it has a string as an input, but the output of this function is another function. It's just a thing. Here is a function with a normal output, but the input is a function. Here is a function with a normal input and a normal output, but there's another parameter, which is another function which kind of controls how the main function works. So you could call this the strategy pattern, the functional version of that. And so here's all the different things you can do with functions. One particular one you can do is you can have a function which has a function as an input and a function as an output, which I'm going to call a function transformer. So the whole job of this thing is to transform functions from one kind of function into another kind of function. That's a really, really important component of functional programming, and we will see one of these later on in the talk. So that's the foundations of functional programming. That's it. That's all you need to know. And you can see, I mean, it's that's the basics, but you can see it can get very complicated. You can have a function that returns another function that has a factory for other functions, and so on and so forth. So yeah, it gets get complicated, but the basic ideas are very straightforward. Right, now we got our functions. How do we compose them together to make bigger functions? Well, let's take two of our functions. We have an apple to banana function and a banana to cherry function. How can we connect them together? Well, what I like about the railway analogy is it's really obvious. You just take the output of the first one and feed it into the input of the second one. And when you do that, you connect them together and you make a new function. And this function turns apples into cherries. And what's interesting is that you cannot tell that it was built from smaller functions. You know, the banana has disappeared, for example. Nobody cares about the banana now. This is a new standalone function which you can use and you can hand around to people. And you can use this as a component in an even bigger function. So you could, you know, have another function which takes cherries as input and combine it with that one. So you can just compose functions just by connecting the inputs to the outputs. And that's all that composition means for functions. So let me show you how this works in C# and F#. And here is some C# functions written as lambdas. Add 1 times 2 and square. Now, if I was going to call these functions in a kind of multiple different ways, I normally have to do this kind of nesting thing. So if I want to say add 1 to 5 and then multiply it by 2 and then take the square, you have to kind of start in the middle and add all these parentheses around the outside. And as they get deeper and deeper, it kind of gets kind of complicated and it can get kind of confusing. So let me show you a different approach that is, I think, less confusing. And this is the piping approach. And this is based on the idea, if you've ever done Unix command line piping, you know exactly how it works. You basically take the input, you feed it into the function, and you take the output. And then you take that and you feed it into the next function, and then you take the output of that, and you feed it into the next function, and you take the output of that, and you feed it into the next function, and so on. So you have a pipeline where the data kind of moves through the pipeline. So hopefully this is pretty straightforward. And I think this is actually a lot easier to understand. Let's look at some code. So in F#, this is the standard way of doing things in F#, which is the pipeline approach. And so this is 5 piped into add 1, 5 piped into add 1, take the output, feed it into times 2, take the output of times 2 and feed it into square. And this is how you would write this kind of chain of functions in F#. And that little vertical bar with an angle bracket is the pipe symbol in F#. The vertical bar on its own, which is what Unix uses, means something else. So it's a slightly different pipe symbol, but that's what it is. And I think a lot of other languages are using this too. Elixir uses it. I'm pretty sure that JavaScript is going to get it too. It's a great way of doing this kind of thing. So you can do this even in C# or Java. It's not as idiomatic, but you can basically write an extension method that does this. So if you do want to do this kind of thing in C#, you can. I think most other C# programmers wouldn't really know what you're doing, but it is totally doable. There's nothing. This is not a language-specific idea. You can do this in any programming language. Right, now, we know how to connect two functions together. How do we build big things from small things, right? So I'll just make up an example of how you can start with a very small thing and build a very big thing. And we will actually see an example of this at the very end of the talk when I build a web service. So we'll start with a low-level operation, like say uppercasing a string as an input and an output. So this is a function, okay? Now, we have a bunch of these low-level operations. And let's say we want to make a service that validates an address. So the input is an address and the output is some sort of result. And inside this service, you combine these low-level operations to do something useful. And I like to use the word service because it's just like a microservice without the micro in front. And I'm over 40, and that's what I'm used to. So there you go. Services. Okay, so we have all these different things, and we combine them into a complete use case, a complete scenario, a complete story, whatever you want to call it. Let's say you want to update your customer data in the database. The input comes in and the output goes out. Now, this is an input-output model. This is not a request-response model, right? So in an object-oriented thing, you'd have a request and a response back. In a functional model, it's an input-output. And so you can chain this, because it's input-output, you can chain this. This is just another function. You can chain it with other functions. Right, so let's say we have all these different use cases or stories, and we want to combine them into a web application. Now, if you think about it, a web application is actually a big function. The input is an HTTP request, and the output is an HTTP response. So it is actually a function with an input and output. So let's model this as a function, and then inside this function, we basically have to choose which one of these stories or use cases to run. So there's a controller or a router or a dispatcher or whatever you want to call it, but there's some way of deciding which one of these things to run based on what the request was. But it's still a function, okay? We're using the same technique at all scales. So if we look at the kind of the insides of a complete web function, yeah, there's branching going on. It's obviously gets kind of complicated, but interesting thing to note is that the data only flows in one direction. Something comes in and it flows through and it comes out the other side. There's no loops. There's no kind of tangled mess of interrelationships. In functional programming, it's very, very common to have this one directional data flow. That makes it a lot easier to understand what's going on. It makes it a lot easier to debug. And it makes it a lot easier to test because you can pull out these little pieces. Each one of these functions is testable in their own right, which is very nice. Okay, so that's the power of composition for functions, the power of composition for arrays, the power of composition for Lego. It's the same idea. We're using exactly the same idea for all three ways of building things. So, right, now let's move on to types. So if you've got a statically typed language, this is the bit you might be interested in. So types are not classes. As I said, they're more like sets. So what do I mean by that? What do I mean by a type? Well, if you think about a function has a set of valid inputs and a set of valid outputs, all the things you can pass in and all the things that are valid to come out. So just think of the set of inputs, right? That is a type. A type is just a name for a set of things. So if we have all the possible integers being the valid set of inputs, we call that type integer. We give it a name, integer. Now, we could also have the set of all even numbers. We could call that type even number. We could have the set of all prime numbers. We can call that type prime number. So there's nothing special about integers. It's just a set of things. We could have all the set of numbers which accept zero, so non-zero integers or something. Now, there's no behavior, right? There's no behavior with these integers. It's literally just a set of things. We can have a set of strings. Again, there's no behavior. It's just literally just a set of strings. We could have all the set of strings that start with the letter A. We could have strings which are 5 characters long. It's just a set of things. It's a set of people, right? They don't have to be programming jargon. They can be anything. A set of people. Here's the set of all fruit. And because it's a set of things, you can have anything in the set. In particular, you can have a set of functions. So this is an example of the set of all functions that turn fruit into fruit. And we write this as the fruit to fruit type. That's the name of the type, fruit arrow fruit. And we will see this also later on. Okay, so these got these types. Now, the thing about types in a functional programming language is they can be composed, just like the railway and the Lego. And this is due to something called an algebraic type system. And algebraic is a bit of a jargon word, so I'm going to call it a composable type system, because that's exactly how we use it, a composable type system. And this is only possible because in a functional programming language, or in this kind of type system, the behavior is separate from the data, right? Because it's just sets of things. You can do set intersection and set union, and you can do Cartesian product of sets. All these kinds of things you can do with sets, and that's how you can build bigger sets and smaller sets. And that's only possible, again, because there's no behavior there. It would be much harder if the behavior was tangled up with the data. So let's look at how you compose things in in an algebraic type system, a composable type system. Well, there's two different ways. You can compose them with and you can compose them with or. And I'm going to use the English words and or because this is how I think of them. So let's look at and. What I mean by composing with and. Let's say that I want to make a fruit salad. I want to model a fruit salad. Well, in English, I would say an apple and a banana and a cherry. I use the word and. And in a programming language like C#, for example, I say, okay, here's the different kinds of apples and bananas and cherries. They're enums. But then I want to compose them together, and I would say it's an apple and a banana and a cherry. So that's how you do it in C#. And what it is just a struct or a record or a class or whatever, a DTO, however you want to call it. It's something with 3 fields, and all 3 fields are required, right? So it's an apple and a banana and a cherry. So this is something that everybody's had experience with. Every programming language supports something like this. And in F#, it's very, very similar. We have something which is called a record, and it has 3 fields. Notice that the types come afterwards rather than before, like in C#. So this kind of looks a bit like JSON. So we'll see some of these in a minute. Now, the other way of composing things is to use or. So in English, I might say I have a snack or a banana or a cherry. Now, you can't really do this in C#, so let me show you the F# way of doing this. I say an apple or a banana or a cherry, and I'm using a vertical bar to mean or. And in F#, I like to call these choice types because we're modeling a choice between different things. It can only be one of these things. It can't be all 3. You have to pick one that is. It's either an apple or a banana. It's not, all of them at once. It's not a field. So these are technically called discriminated unions or sum types, SUM. I like to call them choice types because that's how I think of them. So you could think of it as almost like an enum in C# with extra information. Right, now, what do we do with these types when we want to compose them? So here's a little exercise for you. Imagine that you want to implement a payment method, and you take 3 different kinds of payments: cash, PayPal, and credit card. And for cash, you don't need any extra information. For PayPal, you need an email address. For credit cards, you need a card type and a card number. You need some stuff. So you've got 3 different choices. How would you implement this? Well, if you're doing object-oriented design, you would probably start off with some sort of base class, abstract base class, or an interface or something, and you'd have 3 different implementations of that interface or that abstract base class. And that's this kind of typical object-oriented way of doing things. Now, let me show you a completely different way, which is the compositional way, where you build things up from smaller things, just like with the Lego. So what we're going to do is we're going to start with the small things. And in domain-driven design, I never use words like string or int. I want to use the same words that the domain uses. So I'm going to use the word email address and the word card number. So I've got some aliases for primitive types. And then I can make a choice. A card type is a Visa or MasterCard. And a credit card information is a card type and a card number. So notice I'm using the word or and. So a choice type using or and a record type using and. And then I can build my payment method. So it's cash or PayPal or card. So it's a choice type with 3 different choices. And in the PayPal case, it's got some email. It needs an email. And in the credit card case, it needs the credit card information. And in the cash case, there's no other information. But I don't have to stop because I can keep adding and adding. This is the thing about composition. I can then use this in another class, in another type rather. So I can make some more helper things, like a payment amount is a decimal and a currency is a euro or a dollar or a ruble. And then I can build a bigger thing, which is an amount and a currency and a method. And I'm now using that payment method that I defined up above. And I can keep going and going and building bigger and bigger types from the smaller types. So this is exactly like the Lego analogy, but now we're building it, we're using it to build types. So this is building bigger types and smaller types this is the power of composition applied to a type system. So, very good. Power of composition. Right, now, these composable types are actually really amazing. First of all, they can be used as a executable documentation, and I have a big, this is one of my favorite things. So if I show you a whole bunch of types, this is a whole bunch of different types here. Can you guess what I'm programming? And I think you probably can. It's something to do with the card game. And what's nice is even if you don't even understand F sharp, you have a good idea of what's going on because all the types are very self-documenting and they're all in they're all in the same place. They're not scattered over 20 different files. So there's one single file I can look at and I get a good idea about what's going on in the domain. And you know, mostly people think about types as data, but you can also model verbs, actions. So for example, here we have some actions, some activities, and we can say to pick up a card, the input is this and the output is this. To deal a card, the input is a deck and the output is a new deck and a new card. You can model not just nouns, but verbs as well. And that's very, very important. So what's very cool about this is we have the entire domain on one screen. And, you know, rather than this is like 9 types, and rather than having 9 different files, they're all next to each other on one page. So I think this is a great way of doing documentation. And if you're a new person, if you're a new member of the team and you come aboard and someone says, you know, find all the payment methods and fix them up or something, you know, it's really obvious what the different payment methods are. I mean, if again, I don't have to go to 4 different files. They're literally all here. I don't have to go to the documentation. I don't have to ask anybody. I can just look at the code and it tells me what's going on. So I think this is a fantastic idea. This is a massive topic. I have a whole talk on this. I have a whole blog post on this, and I have a whole book on this. So if you're interested, check out my book. Yeah, people seem to like it. Right, now let's look at some real examples. Let's start off with doing a very simple piping example for Roman numerals. Okay, so here's some Roman numerals. How do I convert an Arabic integer into Roman numerals? So I mean 5 becomes V and 12 becomes X11 and 107 becomes CV11, CV11 I should say. So that's the kind of thing. This is a very standard exercise. Now we're going to do it using the piping approach. Now, in order for that to work, I'm going to show you a slightly different approach than you might be used to, which is going into the fundamentals of how Roman numerals came to be, which is this tally system. You basically make marks, and when you've got 4 marks, then you put a slash through it, and then you just make marks on a tablet or on a wall or however you do it. I think this is how they evolved, and so we're going to do exactly the same approach for our design. We're going to start off with n copies of an I. So if you have, 37, we'll have 37 little scratches. And then every time we see 5 scratches, we'll put a V there. And every time we see 2 Vs, we'll put an X. And every time we see 5 Xs, we'll use an L, and so on and so on. So this is the design we're going to use for our Roman numeral algorithm. So how does this convert into a piping model? Well, it's really easy. We start off by replicating the number, and then we do a replacement. We replace the 5 I's with the V, and that gives out another string. Then we replace 2 V's with an X. That changes another string. We replace the 5 X's with an L, and that is another string. So we're just passing a string through each section of the pipeline. So that's the design, the piping model. Let's actually look at the code. So we'll start with the C# code. So what I'm going to do in the C# code is define a little helper function for each step. And these are going to be nested internal functions inside the main method. Okay, so we start now. Once we've got the helper functions, we can say, make the string however many times, and then pipe it into the first function, pipe it into the second function, pipe it into the third function, and so on and so forth. So we have the helper functions, and then we use them in the piping logic. Now, this is a little bit ugly, and I'm going to make a better version of this very shortly. We can do exactly the same thing in F#. We have these little helper functions, and we define them underneath the main one, and then we define them that we use these helper functions in the main pipeline. So that's the concept of doing a pipe. So that's pretty straightforward. Here's the problem. Okay, it's not always this easy. Like most things, it's like, yeah, it's easy if it all works out, but what happens if it doesn't work out? So so far we've had these functions with one output and one input, and when we want to compose them together, they just connect up very easily. That's all good. But that's not always the situation we have. Sometimes we have a function with two inputs, and we have another function with one output, and we want to try and connect them together. And how does that even work? So this is a problem. How do we compose these things? So now let's look at currying. We're going to take the same Roman numerals thing and we'll just tweak it to use a different technique. So we use this replace function a lot. And this replace function actually has three inputs. The proper input string, and then the two values that to find and replace. And the output is another string. So let's look at, if we want to just use these in line without having these helper functions, could we do that? Well, no, we couldn't, because these replace functions cannot be chained together because it has three inputs, and that doesn't work. So can we fix this problem? And, you know, these composition patterns are really great when functions have one input and one output. But they don't work when functions don't fit that pattern. So you might think, well, this is really bad. That's a shame. But there's actually good news. The good news is that every function can be turned into these one-parameter functions. So there's a trick where you can make every function into a one-parameter function, and then the composition works great. And that's what we're going to do now. We're going to do this trick. And this trick is called currying, named after Haskell Curry, even though he was not the person who invented it. And nothing to do with Indian food, it's to do with a person. So here we have an uncurried function, which is an uncurried function is a function which has multiple inputs, right? And what we want to do is transform it into a function that has one input. Well, how can we do that? What we do is we make a function with one input, and what it spits out at the other end is not the original thing, but another function. So we have the first function takes one input, and it returns a lambda or another, an anonymous function, and that other function has one input, which in this case is b, and then that it returns the c. And you can keep doing this as many times. If it has three parameters, you can have the second one return another intermediate function, and so on and so forth. So this is a bit of a strange thing to get your head around, but it works really, really well for doing the kind of thing that we want to do with multiple inputs. So curried functions are basically a function where every part of it has been turned into a one input function. And then it's a one input function, so we can use composition. Okay, so let's actually see what this looks like in practice. And this is why this understanding functions as inputs and functions as outputs is such an important idea, because we do this a lot in functional programming. Right, one input here, one input there. So we've solved, instead of having two inputs, we now have two functions, each with one input. So don't worry if you don't understand this. It definitely takes a while to get your head around if you're new to this kind of thing. Right, so every function can be converted into a series of one input functions this way. All right, let's look at an example. So here we have our three input function called replace, and it's an object-oriented function. So the third input is actually the object that it's being called. So this is a kind of a three-parameter function. And what we want to do is fix it up so it turns into a one-parameter function. Now, what we're going to do here is have a new thing called replace, and it is going to return a lambda. Okay, so we're going to pass in two parameters, these two parameters, but not the third parameter. And the output of this function is going to be a lambda, not a value. So we're returning a one parameter function. So what we're doing here is this new one parameter function can be chained together because it has one input and one output. So this is the trick. This is the way of kind of currying the replace function so we can use it in our pipeline. So let's look at how we could do this in C#. So this is our curried version of replace. And it looks a bit more complicated, but we only need one of them. We don't have to have 5 helper functions. We just need one helper function now. And now in the pipeline, we can call replace with different parameters over and over. So again, this returns a lambda, which can be used in the pipeline. And we're passing in 2 of the 3 parameters in the helper function, and it returns a lambda. And where does the input from the lambda come from? It comes from the pipeline. So this is using a curried function in a pipeline, and this is why curried functions are so important in functional programming. Let's look at the F# version of this. Now in F# you don't need a helper function because everything is curried automatically in F#. So we can just take this replace function and use it as is without any helping. And so this is one of the nice things about a language like F# is you don't have to do currying. Every single function is automatically curried. That's very nice. So again, we're passing in 2 of the 3 parameters. Where is the other parameter coming from? It's coming from the pipeline. Now, what we're doing here is actually a technique called partial application, which is a really important technique, and it's very, very closely related to currying. It's not the same as currying, but it's related to the idea of currying. So let me give you an example. Let's say we have 2 functions, add and multiply, and they both have 2 parameters. Now in a pipeline, what I can do is just use one of the parameters. So if I say add 2, I'm passing in one of the parameters. Where is the other parameter coming from? It's coming from the pipeline. So I'm basically passing in one of the 2 parameters. And similarly, when I'm passing in one of the 2 parameters here, that is called partial application. So I'm only partially providing the parameters, and the other parameters have to come from somewhere else. And that's a really, like I say, this is a very common technique. And this only works because the functions are curried. So currying means making a bunch of one parameter functions, and then partial application means putting some of the parameters back, but not all of them. Some of them, but not all of them. So you'll see this. This is like I say, this is like super common technique in functional programming. So if you look at our replace thing that we did here, that's what we did. We passed in 2 of the 3 inputs, and we sort of baked it in to the function here. We're passing in 2 of the inputs, and the other input is coming from the pipeline. So this is partial application in our Roman numeral example. So one of the great things about the pipeline approach is they are extensible. So Roman numerals, if I need to add a new feature to the Roman numerals, I can just add new things. I can say I can handle the 9 case and the 4 case. I can just add new features without touching the other features. So a pipeline-oriented approach is really nice because I can have confidence when I add new functionality that I'm not breaking anything else when I add new segments to the pipeline. So this is another reason why my piping model is a really nice way of, if you can try and get your code to work in this pipeline model, there's a lot of other benefits as well. Okay, so this is our challenge. How do we compose a function with 1 output and 2 inputs? And the answer was currying and partial applications. So that challenge has been solved. Good. Right, now let's look at another challenge, which is a function with 2 outputs. So some functions have more than 1 output. And how do we connect that to a function with 1 input? And I'll explain what I mean by more than 1 output shortly. And the challenge is, how do we compose these kinds of things? And the answer is monads. More specifically, there's a function called bind. for connecting these kinds of functions together. So I'm going to use FizzBuzz as our example here. Here's for FizzBuzz. People aren't familiar. FizzBuzz, you need to print fizz if it's divisible by 3, buzz if it's divisible by 5, and so on and so forth. Otherwise, you print the original number. All right, now in F#, we can have a very simple implementation. If it's divisible by 15, print FizzBuzz. Otherwise, print fizz. Otherwise, print buzz. Otherwise, the original number. So that is the kind of standard implementation that you might write if you're an imperative programmer. And there's our we need a little helper function that does the is divisible by. Okay, we're not going to do that because this is too easy. We're functional programmers. We need to make it more complicated. So I'm going to make a more complicated version of FizzBuzz. I'm actually not going to make it just for the sake of it. I'm going to make it to show you how you can do composition out of something like this. This, as it stands, is not composable, and I want a composable version, a pipeline version of FizzBuzz. So here's how you might do FizzBuzz as a pipeline. You say, well, I want to handle the first case, and then I want to handle the second case, and the third case, and then finally, the last case. So I want to do a pipeline. So let's see how we can implement a pipeline for FizzBuzz. So when we handle a case in FizzBuzz, there's two choices for the output. We could either say, well, it's unhandled, like 2 or something, or 7 or whatever. None of these are handled, or it is actually handled, in which case we get a string back. So we have two choices for what this function returns. It's something or something. Something or something. That makes me think I need a choice type. So from a railway-oriented point of view, we now have an input, and we have two kind of branches on our railway track. It's not just a one-track function now. It has two possible outputs. And this is different from what we've seen before. So how can we model this in code? Well, I'm going to create a type which is a choice. It's either unhandled or it's handled. If it's unhandled, we still have the original integer. And if it is handled, we now have some sort of string like fizz or buzz or something. So we have a choice type. This is why they're very good. And I stole this from Reginald Braithwaite. So there's a credit there. Let's see how we actually write the code to handle it then. So we handle it. If it is divisible by the thing, then we say, okay, we're going to make the handle case happen. It's the label, the fizz or the buzz. And if it isn't divisible by the thing, we're going to return the unhandled case, which is the original number. So we either return the label or we return the original integer. So we got two choices in our return. Okay. Now notice that this is a 3-parameter function. Pay attention to that. Okay. Now let's actually test it out interactively. Now the nice thing is these pieces are independent. They're standalone, so we can test them on their own. So we can try handling 12, and it says that's good. That's fizz. If we put 10 into that one, for 3 is unhandled. But if we put 10 into the 5 one, it is handled. So we can test out the little code. Each of these components is independently testable. And notice that we've only got 2 parameters here. And I said it was a 3-parameter function. Where's the third parameter coming from? It's coming from the pipeline. Okay. So this 2-parameter function, when we bake in 2-parameter functions, we now 2 parameters. We now have one of these kind of switch or points type railway track with 1 input and 2 outputs. Okay, so if we try and do an implementation like this, we say, well, if it's handled, we're done. If it's unhandled, we try and handle 3. Okay, if it's handled, we're done. If it's unhandled, let's try handle 5. If that's handled, we're done. Otherwise, we do the last thing. This is a really, really ugly implementation, but you often see this kind of thing when you have nested, when you have kind of different kinds of results that you can return. So let's try and get rid of this ugly code. There's actually a pattern here. It's not, I don't know if it's obvious, but here's the pattern. Every time it's unhandled, we do something with the unhandled value. Well, if it's handled, we're done. If it's unhandled, we do something. If it's handled, we're done. If it's unhandled, we do something. So that's the pattern. If it's handled, we're done. If it's unhandled, we're going to do something. So let's turn this into a helper function. If you think of it going to the railway oriented example, it's like if it's unhandled, we call the next function, but if it's handled, we bypass it. So that's what's basically going on. From a railway point of view, that's how we can think about it. So let's write a little helper function that's going to do this for us. So if unhandled do, I'm going to call it. So if we're handled, we leave it as handled. If it's unhandled, we're going to do something. Now, what are we going to do? I don't know. It depends. So I'm going to just say some arbitrary function f. Well, where does this function f come from? It comes from a parameter. So we're going to pass in a function parameter that controls how this function works. And that was exactly what I was talking about at the beginning of the talk. So, and I'm going to call it f because I have no idea what this function is. I can't think of a better name for it than f. Right, so if we have this new helper function, we can write unhandled do. We can change our logic and we say, well, handle 15. If it's still unhandled, handle 3. If it's still unhandled, handle 5. And if it's still unhandled, do the last step. So each of these little steps is one of these branching railway things, and we can chain them together now using this if unhandled do. The last step brings the two tracks together and basically says if it's handled, that's the string, and if it's unhandled, we just turn the integer into a string. So it converts both sides into a string. And this is composable, unlike the original version, because we can handle new things. We just stick them in the pipeline, and we're not touching any existing code. So this is a much more safe version of FizzBuzz than the original version. We're guaranteed that we add new features, we're not going to break anything. Now, obviously, FizzBuzz is a very silly example, but you can think of a more complicated thing where turning it into a composable thing like this makes it much more extensible and much easier to understand what's going on. Now, let's look at another example, which is chaining tasks. Often you have tasks, you know, when the task completes, you do something else, but when the task doesn't complete, you skip it. And, you know, promises, futures, whatever you want to call them, the same idea. You need to chain these things together. Now, if you look at the kind of code that you often see, you start a task, and when the task is finished, do something else. And when the task is finished, do something else. And when the task is finished, do something else, or promises or whatever. This is really ugly. However, we can use the same pattern. When it's finished, do something. When it's finished, do something. When it's finished, do something. And let's write a little helper function for that. When it's finished, do something. Now, what is it going to do? I'm going to pass in a function parameter. I don't know exactly what it's going to do, so I'm going to pass in a function parameter that's going to do it for me. Okay, so that's parameterized. And once we have a helper function like this, we can rewrite the code to be much more linear, much more in a straight line. And so this is, again, this is a really useful approach for tasks. And you'll see this, I think in JavaScript, there's something called and then, which is exactly the same thing as when finished do. And this brings us to monads. So why monads? Well, what we want to do is a general solution or a general way of thinking about handling functions like this. And there's a way of thinking called bind. And bind is sort of the generic name for the function that composes these things together. So if we go back to the railway analogy and we want to connect these things together, how do we compose these? Well, we compose them into a two-track model. So that's before and that's afterwards. And I call this the two-track model, otherwise known as railway-oriented programming. And I have a talk on this one too. So that's the idea. If we have a two-track model, we can connect these things together. But here's the problem. Composing one-track functions is easy. We connect the inputs to the outputs. Composing two-track functions is also easy. We just connect, the corresponding inputs and outputs. But we don't have that. We have one input and two outputs, and they can't compose. So what we have here is a function like this that is not composable. However, if we had a function like this, a two-track function, this is composable. We can connect these ones together. So now our problem is, how do we go from the before case to the after case? How do we transform the top function into a function that looks like the bottom function? And now this is where bind comes in. So bind is the name for a generic kind of adapter block that solves this problem. And if you're using the model railway approach, you often see this kind of thing. There's a two-track system and there's a slot on the top where you fit your model railway. So we have a slot for a function. We pass in our switches or points function. We put it in the slot and it comes out as a two-track function. So that's what I call a function transformer. A function comes in and it comes out as a different shape. And the new shape is a much better shape, much more usable shape, because we can compose these shapes together. So the implementation is really easy. It's a lot more complicated to explain it than it is to write the codes. So if we use the FizzBuzz example, it comes in on a two-track. If it's unhandled, we do the next function in the track, and that's fine. And if it was handled already, we just don't do anything. We just return the original value. So that's as bind for the FizzBuzz. Now, if you notice carefully, this is exactly the same as the if unhandled do function. It's exactly the same design. So bind and if unhandled do are the same thing. So bind often has many, many different names. For example, it's often called flat map. Sometimes it's called and then. And in C#, it's select many. There's lots of different names for the same, but it's the same concept. It's a way of chaining functions together like this. So in functional programming terminology, we have something called a monad. And a monad is actually not as complicated as it might sound. It's really just a data type and a bind function and some other stuff. So a data type like FizzBuzz results, where it's handled or unhandled, or a task. And the bind function, in our case, it was if unhandled do, or for the task, it was when finished do. So it's a data type and an associated function. It's a combination of those two things. That's what a monad is. And sometimes you'll hear the word monadic function. And a monadic function is one of these switch points functions, and we use bind to compose them. So in our case, in this FizzBuzz case, it was the handle function. It was one of these switches with one input and two outputs. So that's what a monadic function is. Right, so this was our challenge. How do we have two outputs and one input? And we solved that with monads. And this is why functional programmers go on and on about monads all the time, because this is a very common situation. And monads is the way of chaining things together where they are the wrong shape. And monads turn them into the right shape where they can be composed. So that's what monads are useful for. Right, now just to finish up, I'm going to talk about building a web service using another kind of composition called Kleisli composition. If we think about our two little bits of railway track like this, which are points functions, if we combine them like this, it's really obvious how to combine them, and then you kind of pretend the middle isn't there, it actually has the same shape as the original function, right? It actually is one of these kinds of functions again, right? So what we're saying here is a way of composing them so that you combine two of these and you make another one which is the same shape. Now that's a very important part, because if it's the same kind of thing, you can keep adding and adding, just like Lego. So if you combine two things and you make something which is the same kind of thing, that's a very powerful concept, and it's a great and very important part of composition. And you can build bigger things from smaller things, because no matter what you do, you always end up something with the same shape. Right. So let's apply this approach to building a web server, a web service, or whatever. So we're going to have something called a HTTP handler, and also known as a web part. Okay. So the input is an HTTP context, and this contains everything about the service. It has the request. It also has the partially built response, the cookies, everything you need to make a decision about what to do. And then what comes out is an asynchronous HTTP context option. And it's optional because if you can handle it, you're going to return something. And if you can't handle it, it's optional. You're going to return nothing. So it's either something or nothing, and that's what optional means. So it's either going to be success or failure. And the whole thing is an asynchronous thing, because you might be hitting databases or hitting a network. Who knows how long it's going to take. So it's asynchronous. Right. So this is the components that we're going to build our web framework from. And if you want to know more about the F# version, search for F# giraffe, and you can see this web framework there. So this composition actually has a symbol with an angle bracket equal angle bracket. It's called the Kleisli composition symbol. And we can combine two things to make another thing of the same type. So that's what we're going to do, just like Lego. It's another HTTP handler. You can keep adding and adding and adding. Right, so let's look at some examples. Here's something called path. And what that does is just check whether the input path matches. So this matches hello. And And if it does match the path, it returns success. And if it doesn't match the path, it's a failure. That's all it does. That's one little component. It's a building block. Here is another one called OK. And all it does is return 200. Okay, so it's another building block. Now we can combine these two building blocks with the Kleisli composition, right? First part will check the request path. The second part will set the response. So we have these two little building blocks. We combine them, and we have a slightly bigger component. And this component will check the path and then return OK. Right, now, another component, another tool is the choose. And with choose, we pass in a bunch of these things. And what it does is it tries the first one, and if that doesn't work, it tries the second one. If that doesn't work, it tries the third one. And if that doesn't work, the whole thing is a failure. So what it does is it combines these things, and it also returns something of the same shape, right? Either one of them works, you get success, or none of them work, in which case you get failure. So that is also the same kind of shape. And we can build that into something. So for example, we could have hello returns OK, and goodbye also returns OK, and now something else doesn't work at all. So we can now pick the first path that succeeds. So now we've got our handlers here for the path handling, and for each path handler we can have a little web component that handles that particular path. In this case, we're just returning hello or goodbye, but obviously it could be a lot more complicated than that. Now here's another one called get, and this returns successful if the request is a get, and if it's not a get, it doesn't. So we can build a get component here. So now this only works if it's a get and the path is hello, then we're going to do the hello thing. And if it's a get and the path is goodbye, it's going to do the thing. And if it's a get and it's something else, it's going to return nothing. So a complete web app looks something like this. If it's a get, do one of these two things, otherwise fail. If it's a post, do one of these two things, otherwise fail. And the entire application is just choosing between the get and the post. So this is our router written in a composable functional way using Kleisli composition. And the entire web application just looks like this. Start the web server with this component. So you can see this is building bigger things from smaller things using composition, just like we did for everything else. And what's nice about this approach is that each of these individual handlers are composable, and they're testable, they're reusable. I could test the path bit on its own. I could test just the hello routing part on its own. I can test the post part on its own. I can test each piece on its own, and then when I combine them, I have high confidence that they will work together. I don't have to be forced to test the entire application in one go. So it's a very nice technique. The Lego analogy is very, very suitable here. So no classes, by the way. There were no classes. There's no factories. There's no proxies, manager classes, all that stuff. It's just pure functions combined together with composition. Right, now when you take the entire web request like this, again, I said it was a function, right? So obviously there's branching and stuff going on, but there's no classes, no inheritance, and it's a one-directional data flow. Yes, that's so nice for being able to debug things. That's the power of composition. So let's just quickly review, and then I'll finish up. So I talked about the philosophy of composition. I talked about using connectable, reusable parts, building bigger things from smaller things. That's the fundamental idea, and we saw this with Lego, we saw it with train tracks, and now we saw it with functions as well. And then the functional principles, you have composable functions, and you have composable types. So these things are designed to be standalone. They're not attached to a class. They're not tangled up with anything else. There's no strings attached. They are completely reusable standalone things. And this is a very powerful concept. You design your function. You assume that other people are going to be reusing your functions, so you design them that way. We looked at various compositional techniques. We looked at piping. We looked at currying and partial application. We looked at composition using bind, which is the monad, scary monad word. And we looked at Kleisli composition. And all these things are different ways of solving different composition problems. So almost everything you do in functional programming, all things like monads and stuff, they're all techniques to solve composition. It's like we want to compose things here's a little way of doing it. We use monads, or here's another way we use carrying, or here's another way, you know. So all the techniques you hear about in functional programming are really to do with getting composition to work. So hopefully this is a very quick whiz through everything. I don't expect you to understand all this stuff, obviously, in an hour. However, hopefully it's been a little bit demystified. And so if you're like Homer, at least you're not scared by it. You can see that there's a, it is understandable. It's not magic. It's not mysterious. It's not mathematical at all. So I would encourage you to go, and do more research on this if you think this is an interesting way of doing programming. So hopefully it's not so scary. That was if you come away less scared by monads, then this talk is a success. So why bother with all this stuff? Like the FizzBuzz, was that actually worth it? And I think yes, there's a lot of benefits to composition. First of all, everything's reusable, everything's testable, everything's more understandable because the data flows in one direction, everything's more maintainable because everything's explicit, and everything's kind of extendable because you can add new parts. There's lots and lots of benefits to this kind of compositional way, this pipeline way of doing things. And the final benefit, I think, this is a different way of thinking. It's good for you to learn new ways of doing things rather than just being stuck in a rut and doing things you're familiar with. Try getting out of your rut and learning a new way of thinking about building programs. So I'm going to put the slides and video up there on my website /composition. Feel free to contact me on Twitter. This is my book again. I have to promote my book, of course. And then thank you very much for coming. I will be taking questions in the Slack channel, and or like I say, or contact me on Twitter. Thanks. I hope you found this useful. I will see you later.